Hello, this is Power and Sample Size in R, Hoteling's T Squared, Part 2, where we're going to go through the R code to calculate sample size for Hoteling's T Squared. Well, the first test is a multivariate mean vector is a constant vector, or is that mean not a constant vector? That's what these two hypotheses are. The test statistic is this quadratic form, where sigma is the sample covariance matrix, x bar is a sample mean vector. And I think in the next week or two, we're going to derive this test. Here's how you calculate the alpha. So this, you pick the f value, central f value, such that it makes this 0.05. Well, here, let's just jump right into it. A is going to be alpha, and power is the power you want. So we want 0.05 and 0.8. The sigma matrix is the estimated covariance matrix, which we're going to estimate to be this. And that means K, we're three dimensions. The shift that we're going to try to detect is 0.6, 1.2, and 1. That makes the lambda del sigma inverse del. We estimate n really low initially, and then we calculate the power. It's 0.1, 10%. That's not enough. So we're going to start incrementing it by 1 until it achieves the power, which then it's a sample size of 11. Now, if you watch part 1, this is using the full covariance matrix in your calculations. But if you don't know that and you use the maximum pairwise absolute correlation, then this is how you'd calculate it. We're going to use the same alpha and power, the same delta or the shift. K is the dimensions, which is 3, and our maximum pairwise absolute correlation is 0.6. And then the lambda, before we had the inverse of the covariance matrix, but now we're just dividing by this, which makes that non-centrality parameter a little bit smaller, and I'd recommend you watching part 1 for more details. We estimate n pretty low to get power. 0.9 is not enough. So then we increment n by 1 and re-examining power, and we get an n of 14, which is kind of neat. If you have a good estimate for the whole covariance matrix, you only need 11. But if you only know the maximum pairwise correlation, this algorithm says you need 14, which ensures that you have enough power, right? Because if we knew the covariance matrix, we'd only need 11. But only knowing partial information, there's only an increase of 3 observations. Now here we're going to look at two mean vectors. Are the two mean vectors equal, or are they different? Test statistic is this. Calculate alpha, which is this cutoff value, like this. Excuse me about that. So this is how we do it. Alpha, and we're going to use the same estimated covariance matrix, sigma. But remember, we have two populations here instead of one in the previous example. K is still 3 dimensions. The delta, the shift between the two mean vectors, is 0.6, 1.2, and 1. Lambda would be this. We start out with a small sample size. Its power is 0.15, which is not enough, so we start incrementing by 1. And then the n is 15. Now that's 15 in each group, so we need a 30 of total observations. Now, if we only knew the maximum pairwise correlation, we'd run this. But instead of using the sigma matrix, we used rho, which is the maximum correlation between the observations. And then we run it through this algorithm to calculate n, and that's 20 per group. Now, if you noticed before, we needed 15 per group. Now we need 20. So that's 10 additional observations for only knowing partial information about the correlation matrix. Now, often we don't randomize in a one-to-one fashion. We might randomize in a 1-to-2 or a 1-to-3, where the three's the active treatment and the one's a placebo. And if we want to test, are the two mean vectors equal or are they different, using a different ratio in each group, what we do is we set it up like this, where K1 and K2 tell us the randomization. So K1 might be 3, K2 is 1. That means we want a 3-to-1 randomization. So this is how we do it. Alpha and pi are the same. We're going to use the same covariance matrix, which is this. 3 dimensions. We're going to use a 3-to-1 or 1-to-3 randomization. We're going to use the same delta, the shift. Lambda is this. And we go through and calculate these. So that is, we need 30 and 10 to achieve a 80% power. Now, in a 1-to-1 randomization, where that's sort of optimal power, we needed 15 in each group. So that's 30 total. Here we need 40. So since we're not in the 1-to-1 and we're in 1-to-3 randomization, we need 10 additional observations. Now let's look at it where we only use the maximum pairwise correlation as opposed to an estimate of the covariance matrix. So we run that in, same 3-to-1 randomization. Start out with the low n and run it through the program, and we need 39 and 13, where before it was 30 and 10. So we need an additional 12 observations, only using partial information. It's a conservative estimate, which kind of guarantees that we have the right sample size for the power that we want. Now, one note here is we could just use this program to do all of them. So here's a 1-to-1 randomization. So we put K1 and K2 equal to 1. And if we run this again and see what we get 15 and 15, which is exactly what we got using the previous algorithm. Well, that's all I have for today. Hopefully you enjoyed this. I sure did. I'll add the program in the comments so you can copy and paste and play with it. And if you have any questions, be sure to ask. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.